Welcome. So we have been discussing so far relativistic quantum mechanics, but we have encountered a lot of problems. It didn't matter if we tried to use the Klein-Gordon equation or the Dirac equation for a single particle. In every case, even if we considered relativistic effects, we ran into some pretty important issues, right? And the main problem was that we were considering single particles. But in both situations, what we were just looking at a particle and then trying to see what happened. But we have to consider that because of the fact that we know that the energy squared is p squared c squared plus m squared c to the fourth, right? This is basically E equals mc squared, but in the case where our particle is not at rest. Because of the fact that energy and mass are equivalent, which is basically what this thing is saying, particles can be created and destroyed all the time. So it turns out that just focusing on a single particle approach was never really an option. It never really made any actual sense. So for that reason, a multi-particle framework seems to be quite natural. Now the issue is, well, how do you even do something like that, right? How do we even have this multi-particle framework? That's actually exactly what field theory is about, right? So far, everything that we have done in the course has been just relativistic quantum mechanics, basically, and it is just now that we're getting into the field part. So what we will do is, instead of thinking, right, previously we had this psi of x comma t, and we even at some point used the notation phi of x comma t. What we are now going to do is use a phi again, but this time it's not going to be a wave function like we had before. Now it's going to be a field. All right, so from now on, our phis are going to be fields, not wave functions, because wave functions described a single particle. Now we have these field things. So what exactly is a field? This is going to depend on x comma t, x here, of course, being the three-dimensional vector. We will often be writing this simply as phi of x, x here meaning all four components, x0, x1, x2, x3. So time is included there as well. All right. So the primary element of our quantum field theory will be the field, which is now going to be this abstract element that is going to permeate the entirety of space. Okay? And what exactly is a field? Again, it is very abstract, but you can think of it basically in analogy with a string. So if you have a string in the real life, right, you can have it just resting, or you can just move it a little bit and bump it up, for example. So in this analogy, our field would be this blue line here. This would be our phi of x, which would permeate the entirety of space. In this case, it is a one-dimensional situation because, well, that's all I can draw. I'm sorry. You can make this two-dimensional if you want. And then here in red, we would have a particle. Okay, so this would be the particle. So as it turns out, particles would be just excitations of this field that permeates the entirety of space-time. Okay, so that is what we have right there. And that, as you can see, easily allows for particles to come up and then disappear once again, of course, preserving some rules that we will see later on. But a field naturally allows for the possibility of multiple particles to act at the same time, or to coexist, or to be created and destroyed. And we will actually see the creation and destruction of particles very, very, very soon. Not in this video, but very soon. Okay, so that is very important. So in field theory, we allow for this exchange between energy and mass. Now, an example of what we have right here is, for example, the photon. So in the case where we have an electromagnetic field, the excitation of the electromagnetic field is what we call the photon, right? So that is just one example of what we have right here. And each field will, of course, also have a particular spin depending on what particle can be generated there. And we will see that all, of course, in due time. So we have just discussed this in very broad terms, so you have some idea of what quantum field theory is and what the point is, right? We saw all the problems with relativistic quantum mechanics. Now we are starting to get into quantum field theory. So to begin studying it, we are going to go to one of the simplest cases, and here we're actually going to go back to the Klein-Gordon equation. So I actually promised you that we would go back to Klein-Gordon because it's actually quite good when it comes to the multi-particle framework. So here what we will do is work with the Klein-Gordon theory, and here we will assume a few things. So in the Klein-Gordon equation, we have a field that is going to be real. Okay, so this is going to be real, so that means that the field is going to be the same as its complex conjugate, and it also behaves like a scalar under Lorentz transformations. So if we have prime denoting Lorentz transformations, then psi prime phi prime of x prime is simply phi of x. So it doesn't change. So that's very important. And something else that's important that we're going to be assuming is that as we go far away, as we go x to in plus infinity or minus infinity, right? As x becomes very large, the field will go to 0, which is also something that we expect. As you go very, very, very far away, there should be little or no influence from that field. So that's something that we really expect. Now the question is, well, how do we work in field theory? Now, in quantum field theory, there are usually two ways to work with your fields, and that's the Hamiltonian or the Lagrangian approach. And actually, we're going to be using both of them. Okay, now they each have their benefits. The benefit of the Lagrangian form is that this is explicitly Lorentz invariant, and that's going to be very useful. So this is Lorentz invariant. But the Hamiltonian will allow us to understand the algebra that we have, give us some very important constraints, and it's also going to be very, very, very important. So the first thing that we will do is try to find what Lagrangian density gives us the Dirac, it is not the Dirac story, but rather the Klein-Gordon equation. So keep in mind, the Klein-Gordon equation was the D'Alembertian plus m squared phi of x. And this, of course, we can write, if you just write the D'Alembertian explicitly, d mu plus m squared phi of x, and this has to be equal to 0. So that was the Klein-Gordon equation that we saw in the past. And now we want to find the Lagrangian density that takes us to this equation. So how can we do that? Well, keep in mind that a Lagrangian or an action should lead us to the Klein-Gordon equation under a minimum action principle. So that is something that you may have seen in maybe like a second classical mechanics course that you took, where you see like Hamiltonian and Lagrangian mechanics. But the whole idea is that if we have an action, now what is an action? In case you haven't seen that, the action is simply an integral through time, so let's say ti and tf, of your Lagrangian. Now we are going to be working with a Lagrangian density. That's simply going to be the integral over all of space of the Lagrangian. So if we write it now, we have the integral ti tf, and also over all of space, but we are going to leave that implicit, so the t d3x of now this cursive L. This is an L written in cursive. I don't have the best cursive, but that's what it is. So we will simply write this as integral ti tf of d4x L. Okay, and this thing right here integrated, so the integral of that is going to be L. Okay, so L is integral over all of space d3x of the Lagrangian density. Okay, so that is what the action is. And the whole point of the action is that if we have, let's here quickly graph it, so we have x and t, and we have here at 0 our starting point, and then somewhere over here our end point. So our particle, if we're going from point 1 right here, 2.2 over there, it can take quite a few paths. It can go maybe something like this, or it can go something like this, right? Or it can go something like this. So there's quite a few different paths that our particle could in principle follow. But as it turns out, in real life, our particle only follows that path which leaves a variation of the action equal to 0. Okay, so in this case, for example, this would be ds equals 0, and this is ds different from 0, and this one is also different from 0. Okay, so the particles in real life, they have to obey that, right? The variations of their action have to be 0. And that is a constraint that allows us to find their equations of motion. And that is what we will apply to the action right here. So a variation on our action, delta S, it has to be equal to 0. This means that a variation of our Lagrangian, right? We have to do a variation to our Lagrangians. We're integrating over time and, well, d for x. And now, well, what does our Lagrangian depend on? Well, our Lagrangian can depend, let's maybe write it here. So our Lagrangian can depend on two things, on our field or on its derivative, on its first derivative. Now this is d phi d mu. Or let's simply write this actually, that will be the x mu actually. So let's just write this as d mu. So it can depend on phi, and let's of course for now keep the dependence. It can depend on the field or on its first derivative. We're not going to take into account higher order derivatives because for the equation of motions, we just need the first one. Okay, this is pretty standard. If you have taken courses in Hamiltonian or Lagrangian mechanics, you may have seen very similar procedures to this. So looking at what we have here, we can do small changes to the Lagrangian by changing the field a little bit or by changing the first derivative a little bit. So in the first case, we can change the Lagrangian, right, with respect to the field by a little bit. So we are going to have a small variation in the field plus, right, we can also change here the derivative. So we can do dl and then derivative with respect to d mu phi, and this can be very confusing. So this notation can be very confusing. This is a derivative with respect to the derivative, okay? And you will see it in action in a little bit, okay? And this would be now a variation of d mu phi. So we have here allowed the possibility for there to be a slight variation, right? We can move from the curve a little bit in either direction, and we of course want to optimize this and find when this combination is 0. So with the first term, there's not too much we can do for now. So let's keep it there. This is d for x, and I'm not going to change this part. So the phi of x, variation of phi of x. And now this second term, we are going to use something very important. So we know, and if you don't, I will prove it in a moment, that the variation of a derivative, let's say dx, right, as long as this is in the same direction, is the same as the derivative of the variation. Okay, as long as it is, again, in the same direction. So in case you don't know why that is, or you don't believe me, let me quickly show that. So the variation of a derivative. So what is this? Well, keep in mind, what is the definition of a derivative? As you may have seen, okay, I guess you should have seen at this point. Let's say that we are in the x direction. This is of course valid for any direction, so dx and dx. So this thing here would simply be phi of x plus epsilon minus phi of x divided by epsilon, and we take the limit when epsilon goes to 0, right? So this is what we've seen is the definition of the derivative. So by using this, we have to take the variation of this. But the variation of something, let's say phi again, this is going to be phi prime minus phi. Here phi denoting, of course, the derivative here. Okay, so by using this, we have the variation of the derivative. So what would be the derivative here? Well, simply what we have up there. So limit as epsilon goes to 0 of phi of x plus epsilon minus phi of x, and all of this divided by epsilon. But now we take the variation here. So that means we have to add the prime on both of these, right? We're taking the derivative of both of those. All right, and minus now just our regular old thing, right? First we have the one with the derivative. So we took this thing up here, just took the derivative of each, and now minus what we had up there. So that would be just phi of x plus epsilon, but let's just add a parenthesis here. So it's phi x plus epsilon minus phi of x. Okay, so now, since we want to now switch the order of the variation and the derivative, we are going to combine, or rather write this and this next to each other and this next to each other. So we get the limit as epsilon goes to 0 of 1 over epsilon, and then we have phi prime x plus epsilon minus phi of x plus epsilon minus phi prime of x minus phi of x. Now, what is this? Right? You can see that this is simply the definition of the variations, what we have inside. And this is simply the variation of phi of x plus epsilon. And then we have minus, right, that minus sign right there, the variation of phi of x. Now, what is this thing inside? Well, if you just put the 1 over epsilon inside to make it very, very, very apparent, this thing is simply the derivative with respect to our variable, in this case x, of the variation of phi of x. Okay, so as you can see, it is perfectly valid to change the order of those two things. So there we go. Let's now go back. So the point was that we can just flip the order of this and this. So this is now the variation, and this is now, sorry, it's the other way around. This is now the derivative, this is now the variation. Okay, so now what we want to do is basically to integrate here by parts, right? We can see that this thing right here is equivalent to the following thing. So if we had the total derivative here of the derivative of the Lagrangian with respect to d mu phi of x times the variation of phi of x, right? If we had this quantity here, I'm just gonna maybe make this a little bit neater. So there. Then what would we get, right? What would that derivative be? So this derivative would be, now the first term would be d mu, this derivative with respect to d mu phi of x, variation of this thing, plus now the first part we leave alone, we don't touch it. I guess I should add of x. And now we get times the derivative of the variation here, which is exactly what we had before. So this second term right here is what we had there, right? So that is the same as what we have down here. So what that means is that if we want to isolate this thing, right, we have the lambda d mu phi of x, d mu del phi of x. This is equal to the total derivative, which is this initial thing there, the lambda, blah, blah, blah. Let me just quickly go through this. And then the variation of phi of x minus, and now we just write the other term there. So this one, and that would be the mu d lambda derivative, the mu phi, and the variation of the field. Okay, so now all that we need to do is plug these two objects in for that. Okay, so that's all we need to do. So of course we already did that here with the first one, so we just need to add the second part. So let's maybe clear some things. So now we write minus del mu derivative of the Lagrangian with respect to the mu phi, and there. All right, so all we did there was just plug it in. Now there is something that we need to consider with respect to the variation that we are doing. So the variation that we are doing, this delta S, the whole point is that when we apply it, so when you have the variation on the fields, we want that at the starting time and also at the end point, we want the variation to be 0. Okay, so that is a condition that we of course want to hold, which is very standard, simply that at the start and end point, they have to be fixed. So we can't move the endpoints. We can only move in between. Okay, but the endpoints, they stay fixed. So that is, it's the same condition that you probably used in your classical mechanics courses, or even if you saw some classical field theory. Okay, so with what we have done now, the whole point is that now we have this total derivative, which is of course easy to integrate, right? It's a total derivative. So let's leave it alone on one side. So we'll have the integral of from ti to tf, d for x of dl, d phi x, this is the variation of the field, minus the mu, dl, d mu phi, variation of the field. And then we still have the other integral, right? So maybe I'll just write it down here actually, so that we don't run into the other things that we have been doing. So now we have plus this part, so that would be integral ti tf of d mu, dl, d mu phi, and variation with respect to the field. But now if we integrate, if we do the time integral, right, then we would have integral no longer with time, but rather simply over space. That's all that remains. Then we would have to evaluate this thing between ti and tf. But our variation is by definition 0 at ti and tf. So that means that this entire integral here is simply going to be 0. Now, of course, this is not a rigorous proof, but it simply gives you an intuition, right? Our endpoints are 0, which is why this surface term is going to be 0. And that's honestly good enough for our intentions, for our purposes. And we are left with this equation right here. So we can now just factor out the variations. So we can just write it here on the side. So variation of the field. And if we want this thing to be 0, because again, we are doing the variation of the action, so of course this has to be 0, then either our variation is 0, which is not the most interesting thing in the world, or the lambda d phi of x minus d mu, I don't know why I said lambda, the else, the Lagrangian of course, the d mu phi of x has to be equal to 0. And this is of course the Euler-Lagrange equation. So this is the Euler-Lagrange equation, but now generalized for our field case. We have not quantized yet. We haven't gone into quantization. We will do that probably in the next video. But this is now the condition that we have. So we want that when we have a Lagrangian density, of course, right? Once we have a Lagrangian density and we plug it in here, we want the outcome, the result, to be the Klein-Gordon equation. That is our purpose. So how do we accomplish that? How do we find the Lagrangian density that gives us, as a result, the Klein-Gordon equation? Well, here we are going to think a little bit of our situation. We have this string, right? And it can be excited and it can give us different particles, right? Different excitation levels. And the vibrations, I'm thinking that this thing right here, it's every single spot on the string could be excited into different energy levels. This kind of makes you think of just a bunch of harmonic oscillators. So for that reason, we could think of the Lagrangian density that it somehow relates to the Lagrangian that we know for a harmonic oscillator, which is mv squared over 2 minus 1/2 m omega squared x squared. So that's what we had before. So now thinking of our current situation, well, this is of course a little bit of guesswork, but also considering that once we apply those equations, or rather that Euler-Lagrange equation, we want to get to d mu minus, or rather plus, sorry, m squared times phi of x equal to 0. So keeping that in mind, we could think of something, maybe like 1/2 of d mu phi, and then have this minus m squared phi squared, and this thing divided by 2. Now, of course, if this is the first time watching, this is kind of out of nowhere, and that's completely understandable if you feel that way. And it is kind of a little bit out of nowhere. It is a little bit of guesswork, right? And in quantum field theory, often you will be building Lagrangians based on, not entirely like this, because we are just starting, so we don't know much. We don't have many tools to use yet, but there will be a lot of Lagrangian building. Okay, so if this is the Lagrangian, well, let's check that, right? Let's check. So let's apply the Euler-Lagrange equation. So for that, we need to calculate two quantities: the derivative with respect to the field, and also the derivative with respect to the field's derivative. So those are the two quantities that we need to calculate. So let's begin with the first one, the one on the left, which is the easiest one of the two. So dl d phi, well, let's take a look at our Lagrangian. Now, this is very important. This is not phi. This is d mu phi. This is the derivative of the field. You can't just say, oh, there's a phi here, I can take the derivative. That is not the case. We are taking derivative with respect to phi. The only phi is over there. So we get minus m squared phi, right? Think of it as if it were x, right? If you had x squared, you get minus m squared x, which is kind of what we have here, okay? Now, this derivative is a little bit trickier, but we can still do it, no problemo. So in that case, the derivative of the Lagrangian density with respect to d mu phi, well, let's see. Of course, here there is no d mu phi, but notice that this thing has the mu up there. So how could we lower the index? Well, I hope you have been watching my previous videos, because we know how to lower and raise indices when we're dealing with tensors. So here we have, well, maybe let's write first the derivative with respect to d mu phi, right? And what do we have? We have 1/2 of d mu phi, and now we can write eta mu nu times the nu derivative of phi. And now it is down here, right? Because these two, when you multiply, the nu's simply contract and you end up with a mu up there. Okay, so that is perfectly legal. Now we can just pull 1/2 and the metric, because this is simply the mu nuth element of the metric. This is simply a number. It is 0, 1, or -1, depending on which element of the metric you're dealing with, right? I usually work in QFT with the metric 1, -1, -1, and a bunch of zeros everywhere else. But there is, of course, a convention where the minus signs are reversed. So -1, 1, 1, 1. It doesn't matter which one you use. But the point is, this is either 0, 1, or minus 1. Okay, so you can just take it outside. It won't be affected by the derivative. Then we have to take the derivative with respect to d mu. Now we have d mu phi here. So we have two terms. So of course we need to here use the product rule. So this first derivative is going to be 1, right? The derivative of d mu phi with respect to d mu phi is 1, right? So this would be 1. So we simply get d nu phi, right? We simply get that part. But then we have plus. Now we keep this intact, so d mu phi. And then we get the derivative with respect, or maybe let's write it like, with respect to d mu phi, I guess that's how we can write it, of, well, d nu phi. Well, what is this? Here it depends. If nu and mu are equal, then this is 1, right? Because it's exactly the same as before. The derivative with respect to d mu phi of d mu phi, which is 1. But if they are not the same, then it is 0, because it is not d mu phi, all right? So how can we write that? Well, we can simply write delta, and here just to keep this mu nu. Okay, so by doing that, the only possibility here is that mu and nu have to be equal, so that means that this here has to be the derivative nu. Okay, so the nu derivative. Okay, so both of these are the same, so we get 2 times that, so we get eta mu nu times 2 times this, it cancels out with the 1/2, and the nu derivative here of the field. But now the metric, what it does here, it's going to raise the index back up, so our result is d mu phi. Okay, so that's what this is in the end. So going back here, this here simply is minus m squared phi, and this thing here is d mu phi. Okay, so now let's check. Let's plug this into the Euler-Lagrange equation. So what we need to do is take minus m squared phi, which is this first term, right? And then we have minus, and now we need to take the mu of this, d mu phi, and this has to be equal to 0. So now we can just factor out a minus sign and rearrange this, and we get d mu plus m squared. This is equal to 0. And this is precisely the Klein-Gordon equation. So we have just indeed shown that the Lagrangian density for the Klein-Gordon equation is indeed this thing that we have found right there. So this is just a little bit of an introduction, right? We are going to continue to work with the Klein-Gordon field for quite a while, and we will be dealing in the next video with quantization of the Klein-Gordon field. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So see you in another video. Thank you very much for watching.